Okay, so today we are going to see some very interesting applications of symmetry in quantum mechanics, and this is something you might have seen before in a different form. Okay, but the advantage here is that we will use the character tables to predict which matrix elements that appear in various quantum mechanical calculations are 0 and which are not 0, and this will also help us identifying which are the spectral lines that will be observed. Okay. In order to do this, I am going to introduce something called the direct products. Okay, this is something we touched upon when we were doing products of vectors. If you remember, when we were doing vector products, we had if you have two vectors A and B. Okay. Okay. And we said that there are different ways to take products of vectors. Okay. You can take a product where A dot B, it is called the dot product, and the result is a scalar. Then you have A cross B, where the result is a vector. And then there is something called A. Okay, this is a direct product. This is called a direct product. Okay. And this A direct product with B gives you a tensor. Okay. So the easy way to visualize this is, if A had components A x, A y, A z, and B had components B x, B y, B z, then this tensor product is can be thought of as a matrix A x, B x, A x, B y, A x, B z, A y, B x, A y, B y, A y, B z, A z, B x, A z, B y, and A z, B z. Okay. So, you can see that this is a very natural way to take the product. So, you take the products one by one, you take all possible products and you arrange them in the form of a matrix. Okay. So, this is called the direct product, and this is something that we will use very shortly. Before we do that, I want to say that this can also be used if A and B have different dimensions. So, for example, if A is an m dimensional vector, if A2 up to AM, and B is a n dimensional vector up to Bn. Okay. So, this is m dimensional, this is n dimensional. Then A cross B, I will say A direct product with B. Okay. This is a Mn by Mn matrix. Okay. So, you represent it by an Mn by Mn matrix, because there are Mn times Mn components. Okay. So, there are Mn different products. Okay, and you can take them in any order. So, you have Mn times Mn components. Okay. So, this notion of direct products is something that we will use very shortly. Okay. Now, suppose we had eigenfunctions psi 1, psi 2 up to psi m, which form a basis for a representation So, suppose they form a basis for the representation. Okay, it could be some irreducible representation. Okay, some representation of the group Okay, then we can write. So, we can write the following expression, that suppose you operate R, this is the symmetry operation. So, suppose you operate R on any of the size, okay, then you will get a linear combination of all the size. So, sum over 1 to m, and I am using I will use Rij psi j. Okay, so I can write it in this form. Now, suppose you had another representation. See, suppose you had yet another representation. Let us say eigenfunctions this set, and you had another set phi 1, phi 2 up to phi n. Okay, so suppose you had a different representation, okay, a different base, okay, for another representation. Okay, then you would write R times phi k is equal to sum over L equal to 1 to n. And now you might have some other matrix elements. I will just call it S L K L psi L. Okay. So, you would have some other matrix elements. So, these are the matrix elements corresponding to this operation in this representation. Okay. So, now you can ask what happens to when you take a product. So, how do you think of direct product? And the direct product is most So, the most natural way to think of the direct product is you just take phi j. So, we say that the psi j's, okay, they form a representation for this group. Okay, so they form a basis, okay, for this representation. Similarly, phi l's form a basis. Okay, so then you can show that the quantity, so the direct products also form a representation. Okay. So, what this means is, suppose I take a direct product like psi I phi k. Okay, so suppose I take psi I phi k, I operated by R. Okay, so if I operated by R, then it is not hard to show that what you will get is the following. You will get sum over L j L. Okay. Then what you will get is R I j S K L, okay, psi j phi k. So, you can see that this has very much the structure of something like this. Okay. So, what you see is that after the symmetry operation, this product, okay, looks like this. Okay, and this and so this quantity is like one matrix element of that Mn by Mn matrix. Okay. So, this quantity Rij W j k is equal to something wrong. Okay, W j L phi L. Yes. So, W I k. So, this should be W I k. Okay. So, on the left you have I and k. Okay. Here you have I j k L, you have to sum over j and L. So, the right hand side also depends only on I and k. So, W I k is R I j S k L sorry. So, you write this as slightly differently, you write it as W I j comma k L. This is a quantity with 4 indices. So, I j and k L, this is just, so we just call this quantity W I j comma k L. Okay. And this is this corresponds to, this is an element of that Mn cross Mn matrix, okay, which and this is one of the matrix elements of another representation. Okay. So, this is a Mn dimensional representation. Okay. So, in fact this particular thing is the basis for Mn dimensional representation. Okay. So you can see this expression very easily. You just take a product of these two, okay, then you will end up with that expression. Okay. So, what this means is that this direct product, this is one element of this direct product, and this direct product serves as a basis for the Mn dimensional representation. Okay. And now what we are going to do is we are going to show that this direct product has some more properties that we are interested in. Okay. So we said that this direct product of psi and phi, okay, that also forms that the direct product of these two basis functions, that also forms a basis function for another representation. Now the question that you will ask, the two questions that will come up with, if it is a representation, is it irreducible or is it reducible? Okay. And the second question is, if it is a representation, what are its characters? So, is the representation given by the direct product irreducible? Is it an irreducible representation? The answer is usually yes, and we will see shortly that in some cases it is not. Okay. Sometimes no. Okay. Next is what is character of any element in this representation? No, usually no. Usually it is not an irreducible representation. Sometimes it is. So So, usually it is not an irreducible representation, sometimes it is an irreducible representation. So, the question is a representation by a direct product an irreducible representation? The answer is that usually it is not, but sometimes it is an irreducible representation. Next is, what is the character or trace of any element in this representation? Okay. So I'll write this way. So, the chi in the, this is the direct product of A and B. Okay, so, you have two representations A and B, and this is a direct product representation. So, if you look at the character of any element in this direct product representation, it is nothing but the character of the same element in A multiplied by the character of the same element in B. So, this is the character of R in representation A, this is the character of R in representation B. Okay. And if you in case you did not notice, these are the things that appear in the character tables. Okay. Suppose you had a character table, let us say you have D3. So, D3 has E, 3 classes, it has E, C3, 2C3 and 3C2. Okay. And the 3 irreducible representations, will be A1, which is a totally symmetric. Okay. Then there has to be A2, which is 1 1 minus 1, and the 2 dimensional representation E, which has characters 2 minus 1 0. Okay. So, these are the characters of these operations in A1, A2 and E. Okay. So, notice that the totally symmetric representation, this is the totally symmetric representation. Okay. So, in this totally symmetric representation, the trace of the character of each of the operations is 1. Okay. Now you can see, suppose I construct a direct product, suppose you construct a direct product using A1 and A2. Okay. So, you can construct a direct product representation A1 A2. Okay. Then you can see the trace of the various characters. So, in A1 A2, chi of identity is equal to 1, chi of 2C3 is equal to 1, chi of 3C2 is equal to minus 1. So, this is same as chi in A2. Okay. And it's clear. So, suppose you construct a direct product representation. Okay. Now, this will be since this is one dimensional, this is also one dimensional. So, the direct product will also be one dimensional, and in fact, the direct product is nothing but A2. That is because this is a totally symmetric representation. Okay. Now, consider A2 times E. Okay. So, A2 times E. Now, the character of identity is 2, character of 2C3 of C3. I shouldn't write 2C3, I should write character of C3, character of C3 is minus 1, character of C2 is equal to 0. Okay. And this is A2E is identical, the characters are identical to E. Okay. And that is because this is a one dimensional representation, this is a 2 dimensional representation. Their direct product will be a 2 dimensional representation. okay, and the two dimensional representation is identical to this E. Okay. Now, we can construct other representation. For example, you can say you can look at E okay, E times E. Now, in this case chi of E is equal to 4, chi of C3 equal to 1, chi of C2 equal to 0. Okay, so 2 into 2 is 4 and you can get 1 and 0. So, this way you can go and construct many such direct products. The dimensionality of EE, the dimensionality of this representation, it is a 4 dimensional representation. Okay, it is a 4 dimensional representation. The character of identity will be 4, character of C3 turns out to be 1, character of turns out to be 0. So, using direct products and clearly, since it is a 4 dimensional representation, it cannot be an irreducible representation, it has to be a reducible representation. Okay, so, this is a reducible representation, reducible 4D representation. Okay, so now there is something that you might have noticed. When you construct direct products, you construct these you sometimes end up with these reducible representations. In some cases, in these cases it turned out to be the same as the existing representation. So they turned out to be irreducible, okay, but in general you end up with reducible representations. Okay. Now, reducible representation, we said that if you have a representation that is reducible, you can sort of break it into block diagonal forms and you can write it as a sum of irreducible representations. Okay, so, reducible representations can be written as sum of irreducible representations. Okay, and this is what we had seen. If you had a reducible representation, then you could make it block diagonal. Okay, then you would say it is a sum of these 4 representations. Okay, and also there is 0 everywhere else. Also, we looked at cases where one irreducible representation might appear many times in a reducible representation. Okay. So now this leads us to something interesting, because you have these reducible representation. On the one hand, they are written as sums of irreducible representations, okay, and so this looks like your sum over j a I j chi. So, you will say we had the expression, the character in the reducible representation is the sum over all irreducible representations of chi of r over all irreducible representations. Okay, so we had an expression like this. So on the one hand, you can take this reducible representation and write it as a sum of irreducible representations. On the other hand, you have this reducible representation which you can sort of factor out into these into products as products of irreducible representations. Okay. So the direct product is like you make reducible representations by taking products of irreducible representations, and the other way you can do is that you can take the reducible representation and write it as a sum of irreducible representations, and both these are so what we want to do is we want to look at how these two things are related. Okay. The point I want to make here is that there are only some representations that can be written as direct products. Okay. Only a certain number of representations can be written as direct products, though all representations can be written as reducible representations, or can be written as sums of irreducible representations. Okay. So this is generally true for any representation. This direct product is only true when you construct your reducible representation using direct products. Okay. So what we want to do now is to look at the relationship between these and see how we can exploit the fact that you can write a reducible representation as a sum of irreducible representations. Okay. And if our reducible representation had the form of a direct product, how we exploit that. Okay. So to see an application, a very simple application of these direct products, let us consider this quantity. Let us consider an integral f of a f of b d tau. Okay. And what we want to think about is these are related to basis functions from two representations. Okay. So we want to think of these as basis, we will eventually think of these as basis functions from two representations. Okay. So now this will be 0. Okay. So an integral like this, so we call this I. Okay. So I equal to 0 unless f a f b satisfies or all symmetry properties of molecule. In other words, f a f b. Okay, so in other words, f a f b has a term that is invariant to all symmetry operations. Okay. So the idea is the following, that suppose you are looking at any integral, okay, then this can be written as a sum of many terms. So your f a f b will look like a sum of many different terms. Okay. Now each term, okay, will be 0 unless it is invariant to all the symmetry operations. Okay. So unless your when you operate this by the symmetry operation, okay, this term is not changed, okay, then it will be 0. Okay. So the point is that f a f b should have a term. Okay. It could be a sum of terms, it could be a sum of terms. If it had only one term, okay, then f a f b would be 0 unless that term is invariant to all the symmetry operations. Okay. So this is fairly obvious to see. I mean, you can think of it as a, when you take a one dimensional integral, okay, and if you have an odd function, then an integral from minus infinity to infinity of an odd function will be 0. Okay. And then you say that the function does not have the symmetry of the space that we are looking at. So same way in this, if your integrand does not have appropriate symmetry properties, this integral will be 0. Okay. So that means this implies f a f b has a term okay. So this term in f a f b, okay, is a basis for the totally symmetric representation. Okay. So in other words you operate by R on this, I will call this f a f b, and I will put a t here. So if you take this term, okay, so this particular term, and you operate it by R, okay, so this is one term in f a f b. Okay, so if you operate it by R, then you get back, so you get plus 1 times f a f b. Okay. So then f a f b is a totally FAFB is a basis for this totally symmetric representation. So, for any operation you get plus 1. So, the character for every operation is just 1. So, then FAFB is a basis for this totally symmetric representation. Okay. So, what we have is that if this integrand, okay, is not 0, if it is not 0, okay, then it has to be a basis for the totally symmetric representation. Okay, and this is the property that we will exploit a lot. Okay. So, unless FAFB is a basis for this totally symmetric representation, this integral FAFB d tau will be 0. Okay. Now, the question is this is something that we are saying about the product. Okay. Now, suppose FA is a basis for irreducible representation A and FB is a basis for IRB irreducible representation B. Okay, suppose FA is a basis for irreducible representation A and FB is a basis for irreducible representation B, then what can you say about this representation AB versus A and B? So, this representation, this direct product representation, so this is the direct product representation Okay. Now, the question is unless this is a basis for the totally symmetric representation, this integral is 0. Okay. Now, what we want to find out is when will this be a basis for the totally symmetric representation. Okay. So, if FA is a basis for irreducible representation A and FB is a basis for irreducible representation A, then this direct product representation contains totally symmetric representation Okay. So, when does it contain the totally symmetric representation? Okay. And this contains a totally symmetric representation. It's not hard to show this. Okay. That means the way you think about this is that this direct product representation is written as a sum of various representations, various irreducible representation, and this contains a totally symmetric representation only if the irreducible representation A is the same as irreducible representation B. Okay. Okay. So, in other words this integral is this is a way of saying that this integral is non-zero only if FA and FB are the same. Okay. So, if A and B are irreducible representations, then this integral is non-zero only if FA and FB are the same. Okay. So, or FA and FB belong to the same representation. Okay. So, only if FA and FB are basis functions of the same representation. Okay. So, if these two are basis functions of the same representation, okay, then this integral will have one term that is non-zero. Okay. And in other words, and that term, that product will be a basis for the totally symmetric representation. Okay. So, this is the basis for the this is the basis for irreducible representation. Okay. FA is basis for irreducible representation A, FB is basis for irreducible representation B, and gamma AB, okay, this direct product representation, it contains a totally symmetric representation only if gamma A equal to gamma B. This is very easy to show. This is just based on this expansion of reducible representation in terms of irreducible representations. What is important is that so you can just look at the symmetries of these basis functions, and you can conclude on the non-zero properties of this representation. So, similarly you can easily extend to integrals involving 3 or more functions. Okay, so I did this for 2 functions, but it's fairly straightforward to do it for 3 or more functions. Okay, and I won't bother doing that. So now let's look very popular application of these principles. So the first one we'll talk about is energy matrix elements. Okay, and these are extremely useful when we are doing calculations of the electronic structure of various large systems. Okay, then you have to calculate a lot of these energy matrix elements, and any input you can take from symmetry that will help simplify the calculations is extremely useful. Okay, so let's look at an application here. See, suppose you have your basis functions psi 1, psi 2, psi I, psi j, and so on. Suppose these are your basis functions. Okay. Now what do we mean by energy matrix elements? You consider integrals of the form integral psi I star Hamiltonian operator psi j d tau divided by integral psi I star psi j d tau. Okay. So you look at expressions like this. This is referred to as Hij. This is matrix element of Hamiltonian, or I will say ijth matrix element of Hamiltonian operator. Okay, so it's the ijth matrix element of the Hamiltonian operator. Now, if your psi j's are eigenfunctions of the Hamiltonian, if your psi j is an eigenfunction of the Hamiltonian, okay, then you can easily show that if psi j is an eigenfunction of H and psi I star psi j d tau is equal to delta ij. That means it is orthonormal. I mean these vectors they form an orthonormal basis. Okay, then Hij equal to E. So H times psi j will be Ej times psi j. So it will be Ej, and then you have psi I star psi j d tau divided by psi I star psi j. Okay, so Hij is nothing but Ej times delta Ij. Okay, so if I is not equal to j, then the integral will be 0. Okay, so you can work it out. You can use such a relation. Now, if in general this might not be an eigenfunction of the Hamiltonian. Okay, so you don't know sometimes it is a challenge in the challenge is to actually find out which is the appropriate eigenfunction. Okay, and so you want to find an appropriate eigenfunction. So if you try some function, it will typically not be an eigenfunction of the Hamiltonian. Okay, and when such terms appear in perturbation theory and variation theory and all methods of approximate methods for calculating structure. Now you want to know, so we want to know when Hij equal to 0. Okay, so when is Hij equal to 0? Okay. So that's a question that we want to answer. Okay. Okay. Now, so we have two functions, okay, psi I, and in general psi I belongs to irreducible representation A, irreducible representation 1, and psi j belongs to irreducible representation 2. Okay. What I mean by psi I belongs to irreducible representation 1 is that psi I is one of the basis functions for an irreducible representation. Similarly, psi j is one of the basis functions for another irreducible representation. Okay. So, psi j, they belong to irreducible representations. Now, Hij not equal to 0 only if psi I and psi j belong to same irreducible representation. Okay. So, that means if these two basis functions are basis functions in this of the same irreducible representation, only in that case will this integral be non-zero. Okay. This is an extremely powerful theorem and very useful result, and we will look at some applications of this. Okay. So, the other very common application is in spectral transition probabilities. Okay, so one application we saw was energy matrix elements. Okay, and in that you can use some ideas of symmetry to find out which of these energy matrix elements will be 0 and which will not be 0. The other application is in spectral transition probabilities, and again the idea is very similar. Okay, so here typically the transition probabilities are there is a quantity that appears called the transition dipole moment. Okay, transition dipole moment matrix, and this is given by integral psi I star mu psi j d tau. Okay, so the ijth matrix element of this transition dipole moment matrix is given by psi I star mu psi j, where mu is a transition dipole for appropriate transition. Okay. And what I mean by appropriate transition is that if we are looking at a transition caused by the electric field, okay, then this will be the electric dipole. Okay. If you are looking at transition caused by the magnetic field, it will be the magnetic dipole. So, whatever quantity couples to the external field is what will appear here. Okay. Now okay, so or this is more this is, I'll write it as H prime. Okay, this is interaction. This is interaction energy for appropriate transition. Okay. This is related to the interaction, okay, that couples that the interaction with the external field or that allows this transition to take place. It is related to the interaction energy for that. Okay. So if we are looking at, so as an example, let us look at electric dipole transitions. Okay, then in this case H prime is equal to the dipole moment operator times E. Okay, so dipole moment operator dotted into E. Okay. Now the dipole moment operator, this is the external field. Okay. And mu, this operator is can be written as sum over all particles, okay. In this case we will be looking at electrons, and what you can write it as, E, which is the charge on the electron, times Ri, which is the position of the particular electron. Okay. And this can be written as sum over all particles E xi. So I will take the E outside, xi I hat plus yi j hat plus zi k hat. Okay. And so this integral involving H prime, the transition dipole matrix, transition dipole moment matrix, okay, that will look like, so transition dipole moment matrix looks like ijth element integral psi I star. Now you have E little e, and what you have is x I hat plus y j hat plus z k hat psi j d tau. Okay. So and then you can write this as three integrals, E times E. Okay. The first integral will look like psi I star x psi j d tau, and this thing multiplied by I plus integral psi I star y psi j d tau. This thing will be multiplied by j plus integral psi I star z psi j d tau, and this will be multiplied by k. Okay. Okay, so this is your ijth matrix element of the transition dipole moment matrix, and this tells you the probability of transition from I to j, okay, or from j to I. Okay, this tells you the probability of transition from I to j or from j to I. Okay. Now you can immediately see that this will be 0 unless one of these integrals is non-zero. Okay, this will be 0 unless one of these integrals is non-zero. So equal to 0 unless one of three integrals above not equal to 0. Okay, so can we say something about which of these integrals will be non-zero just based on the symmetry properties of psi j and psi I? Okay, so let us take example again. Let us take integral psi I star x psi j d tau. So the question is, when is this integral equal to 0 and when is it not equal to 0? Okay. Now if this, So if this transition dipole is non-zero, if this is not equal to 0, then we say that the I to j transition, okay, is allowed with x polarization. So I to j transition with x polarization is allowed. Okay, so that's what you say in this case. And so the question is, when is this I to j transition with x polarization allowed? So if above integral is non-zero, we say that the transition from state I to j is allowed with x polarization. Okay. So the question is, when is this allowed? And the answer is actually very it looks very simple, but it should be fairly obvious when you it should be fairly obvious to see. So integral is non-zero if or only if the direct product, okay, psi I psi j, okay. So the direct product representation psi I psi j, okay, is same as x or contains x. Okay. So what I mean by same as x or contains x is that same as that, this means the in other words, the direct product representation is same as or contains IR, the irreducible representation to which x belongs. Okay. And if you recall, you have E 2 C3 3 C2, okay, and you typically have A1 A2 E, okay, and you have all these characters 1 1 1 1 1 minus 1 2 minus 1 0, okay. And on this side what you have here is x y z r x r y r z, okay. Now if your direct, suppose let us say x y, let us say you have x y r x r y, right, and let us say this is z r z, okay. So if you had something like this, then what you see is that x and y appear in this representation, in this irreducible representation, okay. So this integral will be non-zero only if the direct product psi I star psi j belongs to this irreducible representation, okay. So only if this direct product belongs to this irreducible representation, okay. And that's again it is something that can be shown fairly easily, okay. So what this helps you is that so now you realize the significance of writing all this x y z here, okay. So you can immediately see which transitions will be allowed with z polarization, which transitions will be allowed with x y polarization, okay. So next we will look at some more applications of this in the next class.